Hello, today we're going to go through the Chapter 13 practice concept quiz on everybody's favorite topic, equilibrium. Question 1. What type of chemical reaction is this? So we have hydrochloric acid reacting with phosphorus pentoxide to produce water and phosphorus pentachloride. So there's quite a bit of information on this slide, but I'm going to start by explaining to you the characteristics of each of these chemical reactions, and from there I'll walk you through how I would use that information to solve this problem. In the top right corner, I've written out the 3 acid-base models you need to know. Starting with the Arrhenius model, Arrhenius acids, such as hydrochloric acid, contain a hydrogen, and when they dissociate in water, they ionize into H+ ions, thereby increasing the acidity of the solution. Arrhenius bases, like sodium hydroxide, contain a hydroxide group, and when they dissociate in water, they ionize into OH-, increasing the basicity of the solution. Now, the Bronsted-Lowry model states that acids are proton donors and bases are proton acceptors. An example of a Bronsted-Lowry reaction would be ammonia reacting with water to produce ammonium and hydroxide ions. In that case, the ammonia would serve as a base, accepting a proton to become the conjugate acid NH4+, and the water would serve as an acid, donating a proton to become the conjugate base OH-. So the last acid-base model here is the Lewis model. Lewis acids are electron acceptors, and Lewis bases are electron donors. When the base donates a pair of electrons, it forms a covalent bond with the acid. And an example of this would be hydroxide donating its electrons to carbon dioxide to form bicarbonate, which is CHO3-. So those are our 3 acid-base models. Now we're going to look at these bottom 2 here, so the redox and the precipitation reactions. Now, redox reactions are not acid-base reactions, but they involve a change in the oxidation state of the atoms involved in the reaction. We know that in a redox reaction, one species is oxidized, meaning it loses an electron, and another is reduced, meaning that it gains an electron. You may have noticed that the equation written here on the slide has been balanced. In order to definitively say whether or not this is a redox reaction, we have to balance the reaction so the appropriate oxidation states can be assigned. If you take the time to calculate the oxidation numbers on each of these atoms, you'll see that there was no net change in oxidation states moving from the reactant to the product side. So therefore, this cannot be a redox reaction. Precipitation reactions involve the formation of an insoluble salt when 2 solutions of soluble salts are combined. Looking at this reaction, I see that we have a solid on the reactant side and on the product side. So this can't be a solubility reaction because for it to be a solubility reaction, we would need 2 aqueous species reacting to form a single insoluble salt. Now, in terms of acid-base reactions, I don't see an increase in hydrogen or hydroxide ions, so this is not an Arrhenius reaction. Let's see if this is a Bronsted-Lowry reaction. I don't see any transfer of protons happening here, so that leaves us with only one other option, the Lewis model. So the Lewis model, like we said, involves an exchange of electrons from the base to the acid. In this case, that is exactly what's happening here. The hydrochloric acid serves as an electron acceptor and becomes phosphorus pentachloride. The phosphorus pentachloride, once it has donated its electrons, becomes water. This is in equilibrium though, so at any point, the electrophilic phosphorus pentachloride can accept an electron pair from the water, which serves as a weak base and weak nucleophile, and become hydrochloric acid. So therefore, our answer here is going to be the Lewis model. Question 2. 37.5 moles of hydrogen gas and 18.3 moles of oxygen gas are in a 29-liter container at a temperature of 246 Kelvin. What is the partial pressure of oxygen? So I always start out these problems by identifying our given quantities. So in the problem, we're given a volume, a temperature, and a number of moles of hydrogen and oxygen. In this case, we're asked to solve for partial pressure. And given that we have these variables, there is one equation in particular that is really sticking in my mind, and that equation is PV equals nRT. So, because we're asked to solve for the partial pressure of oxygen specifically, the information about hydrogen is irrelevant, so we're not going to use it to solve for the partial pressure of oxygen. When we use this formula, there are certain units that we need to apply in order for it to work. And pressure will be measured in pascals. Volume will be measured in meters cubed. Temperature will be in Kelvin. And then we know that N is number of moles. And then R, the gas constant we're going to use here, is 8.314 joules per mole Kelvin. So it's important that you use these units because otherwise your answer is not going to be accurate. So we'll start by rearranging this equation to solve for P. We have P equals nRT over V. Now I said that volume needs to be expressed in terms of meters cubed. I know that in 1 meter cubed there are 1,000 liters. So if we have 29 liters, then that means that we have 0.029 meters cubed. We are asked to report our answers in terms of atmospheres, but we'll just do that at the end. So we have our number of moles of oxygen, 18.3, times 8.314, times 246, divided by 0.029 meters cubed. So when you punch that into your calculator, you should come up with an answer of 1290619.49 pascals. So to convert this value to atmospheres, we'll say that this many pascals multiplied by 9.87 e to the negative 5 atmospheres divided by 1 Pascal will be equal to 12.7 atmospheres. And in this case, we need to report our answer to 2 significant figures, so this will be approximately 13 atmospheres. So this is our partial pressure of oxygen. True or false? The equilibrium constant expression for this reaction is written correctly. So to determine whether or not this is written correctly, we need to know that in a proper Kp expression, the products are always drawn over the reactants. And no liquids or solids should be included. So now if we refer to the Kp expression given to us in the problem, we see that the products were written over the reactants, so that checks out. There are no liquids in the chemical reaction, so by default that checks out. However, there is a solid in the reactant side. So theoretically, if this Kp expression were written correctly, that would not be included in the expression. However, they included it, so therefore the answer to this is false. But to make this expression true, all we would need to do is eliminate that solid from the expression. Question 4. For the reaction 2D going to Z, if Kc equals 16, what will happen to the reaction if the concentration of D is 0.25 and the concentration of Z is 2.0. To solve this question, we first need to solve for Q. So we can solve for Q by setting the concentration of our products, Z, over the concentration of our reactant, D. In this case, there's a coefficient of 2 in front of D, so we need to raise the concentration to the power of 2. When we plug in our numbers, we'll have 2.0 divided by 0.25 squared, and that will give us 32 for Q. Now, if we know that K is equal to 16, we can see that K is less than Q. Now I'm going to show you a little trick that never fails, but in order for this to work, you have to draw the K first, and you'll see what I mean in a second. So if K is less than Q, the reaction is going to shift to the left and make reactants. If K is greater than Q, the reaction is going to shift to the right and make products. Finally, if K equals Q, neither side is favored over the other because the reaction is in equilibrium. So that trick I was telling you about, this little less than sign, if you write K first, the sign of inequality will point towards the direction in which the reaction is going to move. So if K is less than Q, this little less than sign is pointing to the left to indicate that we're going to make reactants, and the reaction is going to shift to the left. And the same way, if K is greater than Q, then that arrow, that little inequality sign, is going to point to the right, indicating that we're going to shift the reaction to the right and make products. So in this case, seeing as though K is less than Q, this is our scenario. We're going to make reactants and shift to the left. Question 5. What is the value of K for the reaction A plus B produces 4 moles of D? This here is our net overall reaction that occurs when we sum together these two elementary reactions. Notice that in the first reaction, we have 1 mole of A plus 1 mole of B producing 2 moles of C. And in our net reaction, we also have 1 mole of A and 1 mole of B on the reactant side. So in that case, we don't need to change anything about that first step in the reaction. However, we need to take a look at the second reaction because we have 1 mole of C reacting to produce 2 moles of D, and we need 4 moles of D. So you can probably guess what the next step is. We're going to take this second elementary reaction and multiply it by a factor of 2. And whatever number by which we multiply the reaction, we need to raise K to the power of that same number. So in this case, we're going to square the K value. And when we multiply this reaction, we will end up with 2C reacting to produce 4 moles of D. And the reason I wrote this out for you is so that you could see that we have 2 moles of C on the product side in reaction 1, and we have 2 moles of C on the reactant side in reaction 2. So they're going to cancel. And now we are left with our net overall reaction, A plus B, producing 4 moles of D. Finally, we can go ahead and solve for our K value. So K is going to be equal to K1 multiplied by K2. So it'll be 35 times 0.91 squared. Don't forget to square your K value. And when you plug that into your calculator, you'll come up with K equals 29. At equilibrium for the aqueous reaction, 2J plus K produces 3L. The concentration of J is 4, the concentration of K is 3, and the concentration of L is 2. What is Kc? So we know Kc is written as the products over the reactants, specifically the concentration of the products over the reactants. In this case, we only have one product, 3L. Because we have 3 moles of L, we're going to take the concentration of L and cube it. We're going to divide that by the product that we get from the concentration of J squared multiplied by the concentration of K. So plugging in our values now, we'll have 2.0 cubed divided by 4.0 squared multiplied by 3.0. So plugging that into your calculator should give you a Kc value of 0.17. Question 7. What is Kc for M plus 2Y producing 3 moles of N if Kp is 550 at 333 Kelvin? So we have an equation to solve for Kc given Kp. That equation looks like this. So Kp equals Kc multiplied by the product of RT raised to the power of delta N, where delta N is the change in the number of moles of gas. So that being said, we have a solid here in our chemical reaction, and that is not going to count in our analysis, so it might as well not even be there. So we're going to rearrange and solve for Kc. So our new equation is going to be Kc equals Kp divided by the product of RT raised to the power of delta N. So we're going to plug in our values now. We have 550 divided by 8.314 multiplied by 333 raised to the power of delta N. So what is delta N? So it's going to be final moles of gas minus initial moles of gas. So we have 3 moles of gas in our products minus 1 mole of gas in our reactants. So it's going to be raised to the power of 2. Plugging that into your calculator will give you a value of Kc equals 0.74. Question 8. What is the equilibrium concentration of ammonia given this chemical reaction and a K value of 3.8 times 10 to the negative 5? The initial concentration of H3C2O2- is 1.25 molar, and the initial concentration of ammonium ions is 2.5 molar. We are also told that there are no products. So to solve for the equilibrium concentration of ammonia, we need to set up an ice table. Starting with our reactants, we are told the initial concentration of H3C2O2- is 1.25 molar. For ammonium, it's 2.5. And because there are no products, the initial concentration of both of these is going to be 0. Now, according to Le Chatelier's principle, if a reaction is in equilibrium and there are more reactants than there are products, like there is in this case, then the reaction is going to shift to the right and it's going to make products. So the change on the product side is going to be positive X, and on the reactant side it's going to be minus X. So now we're just going to combine the initial concentration and the change for our equilibrium expression. So 1.25 minus X. For ammonium, it'll be 2.5 minus X. And it's just going to be X for these products. Now we need to set up an expression using our given K value. 3.8 times 10 to the minus 5 is going to be equal to the equilibrium expression of the product, which in this case is X squared, divided by the equilibrium expression of the reactants. So 1.25 minus x multiplied by 2.5 minus x. Because our K value is so small, notice that it's raised to the power of minus 5. When we subtract x from 1.25 or from 2.5, the change is nominal, so we might as well not even include x in the denominator. This is what is known as the small x approximation, and it makes our lives much easier when trying to do this calculation. So instead, we're just going to have 1.25 multiplied by 2.5 in the denominator. Now you just want to get the product of these two numbers. Once you have that product, you're going to multiply that number by the K value. And then finally, you'll take the square root of that, and whatever value you get will be equal to x. So in this case, x is going to be equal to 0.011. And just as a reminder, we're solving for the equilibrium concentration of ammonia, which is right here. And the equilibrium concentration is equal to x in this case. So therefore, x equals 0.011 molar. That is our final answer.